Let's look at the negation of quantified expressions. Here's an example. Every student in your class has taken a course in calculus. We want to negate this statement, but before negating that, let's identify the constituents. So our statement P of x can be written as x has taken a course in calculus. And hence, the statement every student in your class has taken a course in calculus can be written as for every x, P of x. Now let's negate that. What we want to do is we want to calculate the negation. First of all, let's see how do we negate P of x. As you've seen in previous videos of mine, the negation can be written in the English language as it is not the case that P of x. Now substitute for P of x in the English language. This statement turns into it is not the case that x has taken a course in calculus. Now the same thing with quantification. When we want to say not for every x, P of x, what we're trying to say here eventually is that it is not the case that every student in your class has taken a course in calculus. Now, logically, what that means, if it is not the case that every student in your class has taken a course in calculus, so this means there must be at least one student that has not taken a course in calculus. Now let's translate this back into mathematics. So there must be at least one student, can be translated as there exists an x that has not taken a course in calculus, is translated as not P of x. And this example illustrates the logical equivalency of this statement. Not for every x, P of x is equivalent to there exists an x, not P of x. Now, this example illustrates the equivalency, but it does not prove it, because proof by example is not a proof. Now, in order to prove this, we need to take a different approach. We need to see when this statement for every x, P of x is always true. We can look at it this way. This statement is always true if and only if for every x, P of x is false. So for this statement to be true, if and only if for every x, P of x is false. If for every x, P of x is false, this means that this is if and only if there is one element, x at least, of course, for which P of x is false. Let me illustrate in a different way. Imagine that our domain has infinite number of elements, and we can number them x1, x2, x3, x4. So this statement over here can be loosely written as P of x1 and P of x2 and P of x3 all the way to infinity. And we know that this is a conjunction statement, a compound conjunction statement, and a conjunction statement is only true when all of these statements are true. This can only be false if one of those is false. Okay? And hence there exists one element, at least, for which P of x is false. If P of x is false for that element, then This means that not p of x is going to be true for that element. So rewriting this and this in math, we can say if and only if there exists an element x, not p of x. And this is going to be true. So combining these two together, we can safely say that these two statements are equivalent, i.e., the negation of for every x, p of x, is logically equivalent to there exists an x, not p of x. And hence we get the Demorgan Law of Quantifiers, which states that, let me write over here, Demorgan Laws of Quantifiers, not there exists an x, p of x, is equivalent to for every x, not p of x, and not for every x, p of x, is equivalent to there exists an x, not p of x. One way to remember this, or make it easier for you to remember, is that the not, when it passes through a quantifier, it changes it to the other one. So when the not passes through the existence quantifier, it changes it to the universal, and if not passes through or jumps over the universal quantifier, it changes it into an existential quantifier, and then the not sets or rests just in front of the logical statement. Let's take a few examples. Let's take the statement. Let me write an example. Let's take this statement. For every x, x squared is greater than x. And we want to negate that. Now to negate that, negation of for every x, x squared is greater than x, can be written as there exists an x, according to the Demorgan law, not x squared greater than x. Now, usually you can stop over here, but since this is a mathematical expression, we can still go further by rewriting it in a different way. We can also say that we can also write it as there exists an x such that x squared is, for example, loosely not greater or equal to x, or you can even rewrite it as for every x, x squared is less than or equal to x, which all are logically equivalent. Let's take another example with the existential quantifier. Let's say we have a statement, there exists an x such that x squared is equal to 2. If we want to negate that, the negation of there exists an x such that x squared is equal to 2 is equivalent to for every x, it's not the case that x squared is equal to 2. Now again, you can stop over here, or you can further go and make this statement a more expressive statement, and you can express this statement by saying for every x, and we negate the, so equal to not equal, and that would be the final answer. Let's take a more expressive example. Let's take the example that we want to negate for every x, p of x implies q of x. Now, when we apply the Demorgan law, this is equivalent to there exists an x, not p of x implies q of x. Now we can further simplify this, or we can further rewrite this using, if you recall, we can use the truth table where the negation of an implied statement can be written as a conjunction between P and not Q. So we can rewrite this as there exists an X. P implies Q, negates to P and not Q. So we can say P of X and not Q of X. And that's your final answer. Let's take an example where we can translate some English statement into math. So here's the example. The statement we have is, every student in this class, has visited either Canada or Mexico. So we need to translate this into math. So the first thing we'll do is we're going to identify the different statements. So let's introduce S of x, which is the statement that x is a student in class. And let's introduce C of x, a statement that means x visited Canada. And we can also introduce M of x as a statement as x visited Mexico. So now, when we write this statement in mathematics, every student translates into, for every x, if x is a student, this implies that the student has either gone to Canada or Mexico. So we can say C of x gone to Canada or M of x gone to Mexico. And that's the answer. Let's look at a set of statements called an argument and see how we can translate that into mathematics. Here are the statements. The first statement says, all hummingbirds are richly colored. The second one says, no large bird lives on honey. The third statement says, birds that do not live on honey are dull in color. And the fourth statement, which is also called a conclusion, is that hummingbirds are small. Let's translate that. Let's define the following statements. Let's define P of x to be x is a hummingbird. And let's define Q of x to be x is large. Also, let's define R of x to be x lives on honey. And let's also define S of x as x is richly colored. Now we can express these statements and the argument, the entire argument, using quantifiers and P of x, Q of x, R of x, and S of x. So the first one, all hummingbirds are richly colored. We can say for every x, P of x, they're hummingbird, then they are richly colored. Richly colored is represented by S of x. So S of x. And our first statement is translated to, for every x, P of x implies S of x. The second statement, no large birds live on honey. So we have large birds, Q of x, and lives on honey, R of x. And when we quantify this, we say no large bird, so there doesn't exist an x such that Q of x and R of x. The third statement, birds that do not live on honey are dull in color. We can say those do not live in honey can be written as not R of x. Right? Birds that do not live in honey are dull in color. If they do not live on honey, then they are dull in color. Dull in color can be written as not S of x. For every bird, if the bird does not live on honey, then its color is dull. And then the last statement can be written as, the last statement says hummingbirds are small, which we can say, which also means that all hummingbirds are small. So for every x, if it's a hummingbird can be represented by p of x, then it implies that it is small. Small can be the negation of q of x, so not q will be in order over here. Now notice one thing, that the imply statement is always associated with the universal quantifier, and the conjunction statement always appears with the existential quantifier.